So, okay. Okay, so thank you for inviting me. I really appreciate it. Um, let's see if I can get in here. Okay. Um, so today what I want to talk about is some innovative technology based on bio-inspired design. Um, just to sort of let you know who I am, some of what I do is I study marine mammals in particular, although I'll study anything that swims. And whether I get in the water with the animals or I'm outside. We'll study large animals also moving on land. So this is a 1-ton elephant seal moving around, and doing some of these studies actually sort of put myself into some danger. So here we have some elephant seals fighting, and then to get a scale in, I have to go into all of these animals, weave my way around, and then go up behind them and hope that they're not going to turn on me. But the main part of this study or seminar is that we're talking about biomimetics, and what we're doing in biomimetics is trying to integrate in what we learn from biological organisms and then put them into some type of technology. And probably the best one that everyone knows about is Velcro, which was based upon burrs going into a dog's fur, and a Swiss scientist noted this and thought it would be a good way to attach things. But we've gone on from there. So up above from the Velcro, we also have Mercedes-Benz tried a concept car based upon the boxfish, supposedly to reduce drag. The bullet train in Japan was redesigned, particularly the front end, based upon a kingfisher, a plunge diving bird, as they were having problems as these bullet trains going so fast were compressing air inside tunnels and would come out with sonic booms, which people didn't like. Speedo has tried to emulate shark skin as a way of allowing for swimmers to go faster. There's even a sort of biomimetic attachment device based on based on remoras. And then the gecko feet, another type of attachment. One of the things that I've been working on, and we may talk a little bit about this, is trying to find an alternative to standard rotational propellers, the lotus leaf effect, self-cleaning, and also structural color based on the nano design of surfaces of biological organisms, such as insect wings, which can develop into new paints as well as also cosmetics. Now, the idea of biomimicry, before the term actually came into vogue, was goes back quite a ways to Da Vinci. Leonardo da Vinci actually was trying to become a military architect. And so in looking at fish in a stream and the water going by them, he figured that maybe a better device than a cannonball, a better projectile, would be these ones that were more aerodynamic. Of course, it took a long time before they were ever developed. Borelli in the 1600s had the idea of a submarine that would be propelled by oarsmen with oars that were like frog feet. And then also they would regulate the buoyancy of the submarine with gas bladders that were like swim bladders in fish. And then 100 years before the Wright brothers took flight, the father of aeronautics, a person by the name of Cayley, was looking for a body of least resistance to make a fuselage for an airplane. And he looked at trout and also a dolphin. Now, particularly what I've been interested in and doing work on is AUVs, autonomous underwater vehicles. what you're seeing in front of you is the General Dynamics knife fish. You can go on the internet and find all the specifics on this. It's basically a torpedo. It's a mine hunter. It weighs quite a bit, which means that to get it into the water requires a lot of personnel and winches and such. It has a large operating time based upon battery life. It can dive fairly deeply. It's very slow, however, and does not maneuver well at all. And the price per unit is about $2.5 million. What we're looking to do is to try and develop biomimetic devices that can outperform this basic AUV. So for this, we have bio-inspired or biomimetic autonomous underwater vehicles, or BAUVs. So in this, we have these biomimetic autonomous underwater vehicles that may look like fish or some other organism that people have been interested in. And it would basically have performance capabilities beyond the present technology, which is in use today. So let's consider the naval requirements, what they would like to see, okay? One thing is they'd like to see something going fairly fast. And as you saw, the knife fish does not go very fast, but it's been reported in the literature that animals like swordfish and sailfish can have swimming speeds, at least for bursts, over 70 miles per hour. Tuna, about 46 miles per hour. Even dolphins, about 31 miles per hour. And even sea lions are going at 12 miles per hour. So these animals have the capability of moving much faster than the present AUV technology. And speed is one thing that the Navy would be interested in. Another is maneuverability, the ability to turn very quickly and also in as small a space as possible. And as you could see from that sea lion whipping around, it can do that. Various fish designs, as we see here, particularly things like angelfish, are reported to have a body that can turn rapidly. And then even things like dolphins and whales have the ability to turn and execute these turns, making very small radius turns, and in some cases doing it fairly quickly. We can get an idea of how quickly animals can actually turn versus the standard AUVs. The standard AUVs are on the bottom here. For turning rate, you can see them as the black symbols. Even the BAUVs that are being developed are not as good as what we can find in animals, which are all the light blue dots here. So animals have capabilities far beyond what the current crop of AUVs or BAUVs can do. Another thing that people would like is efficiency, because that's going to relate to battery life and how long we can operate that AUV. The cost of transport, which is the energy cost to move a unit mass, a unit distance, is lowest for fish. And that's this black line on the bottom here. But what we see is that animals that are swimming submerged by the red dots, which include things like dolphins and whales, are actually close to that line. Animals at the surface are much higher because of extra wave drag and such, but then our BAUVs that have been tested, and there's data on, are still not quite there. They're not as low as what we find for submerged swimming animals. So animals, again, are much better at conserving energy and extending their battery life. Another consideration is stealth, okay? Propellers, which we rely upon quite a bit, can cavitate, particularly at high speeds. And animals like this sea turtle here, I've got some background noise. If everyone can mute their mics, please. The type of propulsion that we see in things like sea turtles and their flippers spreads out the load, so we never get close to cavitation. These animals can blend in with the natural scenery and even hide under sand, and also produce very narrow wakes, even when it's illuminated by bioluminescence. In this way, they can sort of hide in the open ocean. Another big one is littoral operation. The current AUVs can only operate in open water, that is the pelagic environment. They can't go anywhere near the shore. They can't deal with large wave action breaking on the shoreline, but marine animals definitely do this. Animals like dolphins and sea lions will actually surf on these waves. So they're much better at this than the standard AUVs. Now, another consideration is scaling. How big can you make it? Obviously, we don't want to have things that are minnow-sized, probably can't do much with them. So we need things that are scalable, will operate at the type of Reynolds numbers that we're most familiar with, probably not getting up to the size of submarines or whales, but being of some sort of size so that they are easily transportable and deployable. This is a consideration. Sensory abilities, okay? We have the ability to detect magnetically things by sonar, but if we're going to build these BAUVs, we need other types of mechanisms that, say, can utilize artificial muscle. And if that's the case, we need proprioceptive type of actions, things where we can actually sense whether the muscle is contracting and how much load it's putting on various elements to activate them. Also, we have things, mechanoreceptors, such as the lateral line system, and even the whiskers of seals have been looking at, particularly the bumpy edges of certain types of seal whiskers, which modify the flow around them. Of course, smell might also be important, and we could look at the inner workings of the shark nasal apparatus. And then, of course, we have sonar in dolphins that is very fine, much better in terms of its fidelity than the sonar that we have. And then the ability to see even in very dark situations, particularly at depth. And then amphibious, we need BAUVs that can not only work in the water, but can then move out onto the land, as we can see the sea lion doing, or even sea turtles will move through the surf and make their way onto land. And then depth becomes important. The article in Nature took everyone by surprise, in which there was a soft robotic ray that could actually go down to the bottom of the ocean, the deepest part of the ocean, the Challenger Deep. We don't have that capability right at the moment, but there are marine mammals, particularly certain types of whales, that can actually go down quite deep in the ocean. And so that ability to work in that full three-dimensional space becomes very important. Now, for me, what I've been working on is with various groups of engineers targeting particular species that would be good for making a biomimetic AUV. And so the sea lion is one, a sea turtle, another, the manta ray, the tuna, and then lastly, we'll talk about the humpback whale, which doesn't make an AUV, but rather shows us a technology that we can integrate into all sorts of human engineered devices. So let's take a look at some of these biorobots that are being developed, in which I've had a hand in providing the biological information on the animals that get integrated into the design of those AUVs. So first one here is a biorobotic sea lion. Okay, the sea lion, as I said, they maneuver quite rapidly. They're fairly speedy. They're amphibious, and they can make their way through the littoral zone. And we've studied sea lions, actually made 3D models of them, either virtually, or we can make also solid models for testing. But working with engineers, Megan Leftwich at George Washington University and Jim Tangora and Harry Kwatney at Drexel University, we've started to integrate in what we know from the sea lines to make a robotic sea line. And so here's the robotic sea line. You can see it has hind flippers that we've been studying for control, as well as the fore flippers for propulsion and maneuvering. So what we envision is that we can create and emulate what we have in sea lines. And so here's our particular robot that's being developed further. And we can emulate the swimming motions of a real sea line. So this is still in development. We're just getting it in the water now, and then we'll be working on the terrestrial locomotion. Another one is ART, an amphibious robotic turtle, and this is with Rebecca Kramer at Yale University. We've been working with her. What we want to do is have an amphibious robot that can swim in the water, make its way onto the land, and then start to walk using legs. So we have then a soft robotic leg. Okay? Here we can take that leg, we can have it inflated and have it as a leg to support the entire weight of the robot, or we can deflate it to make it into a flipper for swimming underwater. So here we can see some of the swimming actions of this robot. Now you'll note that because we have to have 4 legs for walking, we also have the option of having it swim with all 4 flippers. And this is something that we'll be experimenting on in the future. At this point, it can walk, although you'll see this video is speeded up a bit because it's still fairly slow. We're still just learning to walk, but we're getting there. Now, efficiency is important. And at this point, what we'd like to do is emulate the swimming efficiency of sea turtles, which is close to that line where fish are. But at this point, we're still up here, particularly for walking and crawling. The walking cost of transport line for animals is down here, and the swimming of the turtle is up here. So we still have a ways to go, but again, we're trying to optimize how this robot moves in order to increase the efficiency of its walking as well as swimming. Now, the manta ray was done in a large project along with Lex Smits at Princeton and Hilary Bart Smith at the University of Virginia, where we went out first and looked at manta rays swimming in the field, as well as also in aquariums, and then started to build a robot. And the robot's based on tensegrity structures in order to actuate the wing-like fins, where we have multiple struts that are jointed, and then by pulling on various cords, we can emulate this up and down motion of that fin, and then produce Mantabot. And here's Mantabot actually swimming in a pool. On the left-hand side, at the very bottom, we show some of the maneuverability of Mantabot. It's not as fast as some animals like the sea lion, but just comparing the size of the circles, it's smaller because the robot is smaller than a standard manta ray and much smaller than Remus, which is the basic AUV design that is currently in operation. So we have this particular structure that has been built and can maneuver as well as also swim through the water. And then lastly, along with Hilary Bart Smith and others, including George Lauder at Harvard, we've developed Tunabot. And in Tunabot, we have a very fast swimming robot. And we can change its efficiency based upon the stiffness of the peduncle, that is the region just anterior of the caudal fin or tail fin. And we can then have it swim in different ways with different efficiencies. And also I've been working on programming it to maneuver around. Here are actual tuna swimming, and they swim and turn in various ways. One way is they glide through the turn. They use that caudal fin as a rudder and simply glide through the turn. Another is powered turns, in which they're constantly stroking their that caudal fin. And the last is what we call a ratchet turn, where they do an asymmetrical stroke very quickly and make very small turns that then are all put together and creates a larger turn for the animal. Now, the question becomes, how do we build an BAUV with all these performance parameters? And the thing is, we can't, okay? Some of these just don't fit with other things. If you want to go really, really fast, your efficiency is going to fall off. If you want to go really fast, you don't necessarily maneuver very tightly, okay? If you're unstable, you may not be able to work in the littoral operation. If you're too large in size, you can't actuate your propulsor fast enough, okay? So there are various things. Also, if you're large in size, it'd be harder to then move on land where you're now dominated by gravity. So all of these things may interact with each other. So we have to consider that any BAUV that we build has to be designed based upon the mission. It is mission dependent, okay? So if you want something to slow and move in with stealth, doesn't attract attention, that may be different than something that you want really speedy and you don't care whether it's moving rapidly and basically people can see it. So these are things that we have to decide on, depending upon what sort of mission or job you want your BAUV to do. Now, getting away from the BAUVs and their design, I want to bring you to the humpback whale, which is a curious animal. It's a baleen whale. It's in there with blue whales and minke whales and fin whales. The species name is Megaptera nova angli, which means giant wing of New England. And you can see that these animals have these enormous flippers, okay? They're wing-like in appearance. Again, the giant wing, okay? The flippers are about 1/3 the body length of the whale. And so for a whale that gets to 60 feet long, we have a 20-foot long flipper. So these flippers are quite prominent. These whales make their living by taking in large masses of water filled with either krill or fish that they then engulf. Now, my first time I actually got to work with a real specimen, I got some humpback whale flippers from an animal that died in New Jersey along the eastern coast of the United States. And I was presented with these flippers, which are each 10 feet long. It was a fairly good sized whale. And I then had to take these back in a very small car back to my lab in Pennsylvania. And the whole rear end of the car went down. These things weigh, probably at least 300 pounds, and had to make it back, and basically then threw them in a freezer and got to work on them with a very talented student who you see on the below right, Jan Battle. And together we published a paper based upon the structure of the humpback whale flippers. Now, I want you to note a couple of things. Is one, the leading edge of these flippers has these very curious bumps on it. And I also want you to note where there are barnacles. The barnacles are on the bumps. You don't find the barnacles on other places, which may infer that there's some sort of hydrodynamic sort of function going on here. So you can see very nicely here those bumps on the leading edge of the flipper. If you make a cross section of the flipper, it has a very nice symmetrical airfoil design. So again, it has this wing-like structure to it. Now, the flipper itself is nothing more than a very big hand and arm, okay? So on the left, you see an X-ray of a human hand and forearm there, okay? It has all the bones, the ulna and radius and the forearm, and then our carpals, the wrist bones, metacarpals make up the palm of our hand, and then the phalanges, the bones of our fingers. Here, if you look at the humpback whale flipper in X-ray, what you find is that one, it only has 4 fingers, and they're all encased in all this fleshy material. And we actually have more bones in each of those fingers than we would in, say, a human hand. But also note, wherever we have joints between all these various bones along the leading edge, that's where we have those bumps, or what we call tubercles. Now, to show you how important having the shape is with those bumps, this is a fetus that I obtained from the Smithsonian Institution in Washington. It's about 1 foot long. Recall that the adult size can reach 60 feet. Here's a 1 foot long fetus, and you can see even at this early stage in its development, we have those long wing-like flippers and those very prominent bumps. So these are important in even the development of this animal. Now, what does the animal do with these large flippers? Well, it's capable of maneuvering and maneuvers quite well. It's the most acrobatic or aquabatic of any of the large whales. And it can use the flippers not only for doing these sort of pirouettes in the water, but also in feeding. One particular way that they feed is by bubble net feeding. They will swim around underwater, releasing bubbles, and that corrals their prey, fish or krill. And then they make tighter and tighter circles and then come up through the middle of those circles and then engulf all of this prey and water, which they then strain out through baleen plates that they have in their mouth. So they need to turn as quickly as possible. And so they'll use those flippers in order to make those turns. Now, if we look at the flippers and look at the placement of those tubercles, what we find is for about 40% of the length of the flipper, those tubercles are rather regularly spaced. As we go towards the tip, they get more and more closer together, but where they are fairly regular, it's about 7 to 9% of span between each of the tubercles. Having some regularity like that, to me, inferred that there was a hydrodynamic function that the tubercles supplied to those wing-like flippers. Now, at this point, as I said, I'm a biologist and I require the use of engineers because they have all the really cool toys and the mathematics to deal with the hydrodynamics. So we start looking at engineering journals and some of the results there. And in one study by a group, including scientists from Notre Dame University and I believe the University of London, they did an interesting study. They took a cylindrical shape and bent it up. And you can see that on the right-hand side at the top. We have a cylinder that's bent, so we have these peaks and valleys. Now, typically, when you present a cylinder in the water, what will happen is it'll produce an alternating set of vortices from one side and then the other. And these vortices are then conducted into the wake. We have what we call a Kármán vortex street. But if we look at the flow behind the trough, what we see is a fairly broad wake with these large vortices. But what we see on the bumps or those peaks there is a very narrow wake. So by even just bending this cylinder, we can see differences in the hydrodynamics and particularly the wake structure. So how does this perform then for a wing-like structure where we have the bumps on the leading edge? Well, excuse me. To answer this question, I became involved with Lawrence Howell at Duke University, and what Lawrence did was in the computer made a more perfect than perfect humpback whale flipper. And with that, he could then make a physical model. We had two models, one with the tubercles, one without the tubercles, and took it to the US Naval Academy to their wind tunnel. And with Mark Murray and Dave Milosevic, ran an experiment there. Oops. So first thing we looked at is lift. How does lift change with the tubercles? And what you can see is that at low angles of attack, there's really no difference between the tubercle model and our baseline model until we get up to high enough angle of attack. And at that point, for the baseline model, we reach our maximum lift coefficient, and then lift falls off in a condition we refer to as stall. But when we had the tubercles, the lift kept on going up and didn't stall until much higher angle of attack. And once it did stall, it didn't stall as dramatically as what we had with the baseline flipper. So we see an advantage here. We get an increase in lift and we delay stall. But do you get something for nothing? Although there are advantages, what are the disadvantages? Obviously, drag must go up. Well, when we look at the drag, what we find is, again, there's no drag penalty here at low angles of attack until we get to the stall condition. And at that point, drag goes up for our unmodified flipper. But the drag stays low because the tubercle flipper hasn't stalled until much higher angles of attack. So there's an advantage here in terms of keeping drag low, having a little extra lift, and delaying stall. Now, other people have looked at foil sections in which they vary the size of the tubercles, and what they found is the same sort of effects. That stall is delayed, although you may not get as much lift. But again, the big thing is that stall was delayed. In fact, in one of them with very large tubercles, you can see it just plateaus off. Now, what's happening? Why does this occur? Well, on the on the left-hand side is a foil section, and using a RANS code, John Riefenberg and Eric Patterson basically modeled this system. And what you can see is that at 10 degrees angle of attack, we have a stall line that's occurring, a separation line, and we get turbulence starting in the wake and separation from our foil. But when we add the tubercles, what happens is now we find that we're not stalling or getting close to it, but we get what we can call a sacrifice separation. We do get separation from the flow that goes into the troughs, and you see that as those large vortices, but it's very organized. It's not turbulent. And so although we get that separation in which we produce these vortices, what happens is as the flow goes over the tubercle itself, however, it gets accelerated because of the way the spin of the vortices are set up, that the flow over the tubercles goes all the way to the trailing edge. And integrated over the entire flipper, we don't get stall. So we can see this and sort of visualize it as we have here, where we get these in the trough, we get these paired vortices, and that accelerates the flow that gets squeezed in between from the crest or the tubercles themselves. To put it another way, it's like a baseball pitching machine or a tennis machine that throws a ball. We have two counter-rotating wheels, and as the ball goes between them, the wheels then accelerate that ball out. And the same thing is happening here. Now, there's another effect too, and that is what we find is that because we have a wing that's canted at an angle of attack, we're going to have a pressure difference between the underside, where we'll have a high pressure, and the other side, or suction side, where we have a lower pressure. And because of that, in a three-dimensional system, you'll then develop a vortex at the tip, which gets convected back. You see this as the contrails on jet airplanes, airliners. The reason for this is because we have this span-wise flow that is taken up towards the tip. What the tubercles do, however, is they act as aerodynamic fences to prevent that span-wise flow and reduce the tip vortex. And we can see this here in the size of the tip vortex between a modified and unmodified flipper. So we have the additional benefits of these aerodynamic fences. We get a more 2D type of flow rather than 3D flow, where we've reduced that span-wise flow. We reduce the tip vortex. We also reduce induced drag, which is due to the tip vortex, and tip vortices are also associated with noise. So we reduce noise. And recent work that's been done looking at tubercles and jet engines has shown a remarkable decrease in noise, overall sound power reduction of 12.5 decibels. So this is quite a bit. Well, what about the whale? I'm a biologist, so I'm really interested in what is the whale getting out of this by having tubercles. Obviously, they're not flying, so they're not going to fall out of the sky if the flipper would stall, but they are hunting. And what they do is they use that wing-like flipper in order to turn. Now, another person at Brigham Young University built some models that were based on a real humpback flipper, tubercles. He filtered out the tubercles, and then he just smoothed the entire thing. And when he did that, what he found is similar results to what we get. There was really no difference between any of these at low angles of attack, but at the higher angles of attack, the original flipper with the tubercles had higher lift and again wasn't stalling until very high angles of attack. So the whale then is getting this sacrifice separation, getting these counter-rotating vortices, which is keeping the flow over the tubercles attached to the wing, preventing stall, or at least reducing it to higher angles. So why do this? Well, the whale has to make small turns, and for that, it uses its flippers, and the whale will bank just as an airplane will bank to make a turn. And it has to bank with an angle of attack on those flippers in order to create the turn. The higher the angle of attack, then the more you can keep your lift without stalling, and you can make small turns then in order to corral your prey. If, however, you lose your lift, okay, you're going to then not be able to have that turn, and you're going to have it with stall if it stalls, so that you then go out tangentially. For people like me living in the northeastern United States, we have to deal with winter and snow. And so imagine you're in a car and you're going around the curve. So long as there's friction with the tires, you can make that turn. But if you lose that friction due to ice or snow, what happens is you go off tangentially from the roadway. You don't follow the trajectory of that curve, and as a result, you end up in a ditch. And that's what it's like for the whale if it's flipper stalled. So the tubercles become very important in maintaining lift at those high angles of attack to make as small a turn radius as possible. So what can you do with this? Well, you can actually take the tubercles and start putting them onto wing-like devices. So you can take the tubercles, you can vary the amount, you can vary the size, you can have them then working on a wing-like structure, on a very fat structure or a very thin structure. And so here's an example. I don't know if anyone surfs, okay, but shortboard surfers do what's called a cutback. They'll make a very quick turn, go down the face of a wave, and then reverse that turn and go up the front of that wave and then back down again. To do that maneuver, they have to have a fin on the end of their surfboard, which acts like a wing and has to keep lift to make that turn without stalling. Otherwise, you wipe out, you fall off the board. So people have put tubercles on surfboard fins, and it has actually improved performance. Two people actually put these onto surfboards and then had novice, intermediate, and advanced or almost professional surfers try them out. They found it didn't make a difference with the novices. They just couldn't do it, make these turns to begin with, but it did make a big difference for the expert surfers. They could get better performance. One company has put it onto a hydrofoil that you put onto a surfboard, so you actually get lift out of the water on this and can go faster because you reduce the drag on the entire system. Lawrence Howell, who's shown here on the left, developed a device with tubercles, these large wings. You strap that onto your legs and you pump it and you can swim. Speedo has actually put the tubercles onto their swim fins as well as also paddles. I don't get any money from them, but they have them out there for at least training purposes. Some people kayak and they put them onto kayak paddles. To anyone who sails, racing yachts, you have to make very quick turns, okay? So you put on the rudder, these tubercles, and that allows you to turn much quicker and in a smaller radius. You can also put it on the keel or the centerboard. A person in Slovenia developed a personal hydrofoil, and his hydrofoils on this motorized device, actually he put tubercles on. Now, this is one you may not be familiar with. This is an ice boat. What you have is runners, which are essentially like ice skates, and you go on ice and you can go very fast, about 70 miles an hour. And this person put the tubercles on his mast. The sail is essentially a wing. And so the mast is the leading edge. And with the tubercles, he was hoping to reduce the drag and go faster. Of course, the idea of putting them on submarines might be of interest to the Navy. They have lots of control surfaces, rudders, dive planes. That has not, to my knowledge, been done, but a high school in New Jersey entered the international human-powered submarine races. And their submarine had tubercles on their rudders and their dive planes. Now, the way this works is this is a two-person sub. You have a pilot who has to follow a line of lights on the bottom of a test facility in Washington, and then a motorman who pedals. They can't communicate, okay? They can hear when to go, and then they're trying to go as fast as possible. And the tubercles were put on because they wanted to be able to maneuver the sub also. Here we have the test at the David Taylor Naval Test Basin in Bethesda, Maryland. This was helped by their teacher, who had been a naval officer on a submarine. You can see him checking here with the pilot, will look through a window. The motorman would be behind them. They're both on scuba that's entirely flooded. They're going to go here and watch what happens, show how well the tubercles work. There's the line of lights on the bottom, and you can see they make a beautiful turn. Unfortunately, they crashed into the side wall of the test facility. They rescued the driver of the sub. He was okay. They got another run here. Unfortunately, in this run, he touched the bottom, which disqualified that run. And then finally, we did get a good run in, and he was capable of, with a human-powered sub, going at about 1 knot underwater. The record is closer to 6 knots. Some German graduate students thought that trucks might have increased drag due to the mirrors that stick out on the side. So they put tubercles onto the mirrors and found that they reduced the drag. McLaren tried this on the race car. Okay, they kept it on for 1 year, but have not, to my knowledge, used them again. There are some bike companies that have tried this. They put the tubercles onto the wheels themselves or on the spokes, or even on the bicycle frame and the seat stand. Tubercles have been applied to jet engine ducts for the intake of air to help control the flow of air as it goes through a bent pipe. If you have probably tens of millions of dollars, a company in the Netherlands developed a biomimetic yacht in which the stabilizers would have the tubercles on them. Of course, aviation, having airplanes with tubercles could do a couple of things. One, it can make the plane safer because the stall on the wings would be at a higher angle. When you take off and land, you're actually exceeding the stall of those wings, and that's why you have slots and flaps. But that weighs a lot. There's a lot of machinery involved there. Imagine if you could get rid of all that machinery, you'd lighten the plane and potentially make it more economical to fly. Here's another type of flight, paragliders. There's a company that actually puts tubercles on the leading edge of their paragliders. Some people came up with the idea that they could have drones with wings that could go and fly through the different atmospheres of the various planets in the solar system and utilize the wavy leading edge of the tubercles. We can put it on propellers, and even there's been on the internet a little project that kids can do, in which they can have tubercled and untubercled little helicopters, or put them on real helicopters. And so this has been tried on Black Hawk rotor blades, and also micro tubercles on a helicopter that you see there that actually flew. That was developed by a German-Austrian group. They can go on to fans, and there is a company in Canada that did at one time put them onto their fans. It was a real win-win, because in order to move the same amount of air, they found that they could have tubercled blades that were fewer than the same fan without the tubercles that had 10 blades. Here we'd have 5. So the manufacturer saves money in the cost of producing the fan. And then the end users, where these fans are and things like auditoriums and barns, okay, had a 25% energy savings and reduced heating costs, as well as 75% quieter, which for the cattle in these facilities make them a little bit better environment for them. We can put them on computer fans, okay, and in order for cooling, tidal current turbines, and then windmills. And this was tested on Prince Edward Island, which is now getting battered by a hurricane, but was found that we could get an actual 20% increase in electrical energy production in a moderate-sized windmill compared to having a blade without the tubercles. And this is done by a company called Whale Power, which I have to say I am also president of. It is a Canadian corporation. So we can take these tubercles and we can put them onto engineered structures and increase the performance, just as we're trying to do with our animals, and integrate in what we learn from them into the BAUVs. But before I go, I want to just leave you with this, that it's important to save these animals. We don't know where the next technological development will come from, where we will get an idea about this. At the beginning of the 1900s, the population of humpback whales was down to 10% of its original population due to whaling practices. If they had gone, we might never have known about the tubercles. And other animals that we would like to emulate, such as manta rays, dolphins, sea lions, all these animals are under threat. So we want to try and conserve, and in this way we can better find out the secrets of these animals and how they get along in the oceans, that we can then utilize this in development of our own engineered technologies. And with that, I'd be happy to take any questions that you have. Thank you.
Thank you, Frank. Thank you. As always, a fantastic lecture.
So let me stop sharing.
Yes. And well, questions?
Hello, sir. I must first thank you very much for such a nice presentation. And I have some questions. Like one is that, is there any particular shape of these sea animals or sea creatures depending on the depth, depth their usual habitat?
Okay, I'm sorry, your audio's not as nice as I'd like. Is there anything about the shape in regard to what now?
Yes, sir. I'm asking that, is there any particular shape of sea creatures or sea animals depending on the depth their usual habitat?
Okay, depending upon depth, not really, although the one animal that I showed there that went to a astounding depth, about 9,000 feet, has a body shape that I would say is akin to an arrow. Okay, so an arrow, actually to have arrows in the background here, an arrow is a beautiful piece of technology. Although we consider it primitive, it's exceedingly good at what it does, and that is it stabilizes something. So if you fire an arrow, it will, and you watch it in slow motion, you actually see it sort of vibrate and whatnot, but then it stabilizes itself, so you get a true trajectory. with the beaked whale, which was the one that went very deep, you have the same sort of thing. The center of mass is closer to the front. The control surfaces, the fins, flukes and such, are all towards the back, just like the feathers on arrow. And so for these animals which dive deeply, they're trying to conserve as much energy as possible because they dive down with a certain amount of oxygen. And so they have to be as efficient as possible. And by diving down, what they do is they don't fluke all the way down, they'll actually just sink. And having this design like an arrow keeps them straight, keeps them diving nice and straight down to the bottom. They can conserve their energy, they can get there fairly quickly. And then once they've fed on things like squid, they can then come up to the surface. So we see things like that. But in general, we don't see anything that we would really call a shape that is designed specifically for going deeper. We have deep sea fishes that are quite flexible. All sorts of animals can be found at the bottom of the ocean. And in some cases, we wouldn't even say that they're well streamlined, but they do function to get there. So really not that much in terms of depth, causing, allowing animals to adapt to a particular shape.
Actually, because I mean, while gradually increasing the depth, the hydrodynamic pressure will exceptionally increases. So, is it anything to do with it, or
Okay, anything to do,
water pressure? Yes,
anything to
the
do,
water pressure.
I'm still sort of missing a little, anything.
He's saying a hydrodynamic pressure will increase the deeper you go. So does that make a difference?
Okay, not really in terms of the shape and action. I mean, the pressure increases, and what we find is certain adaptations, not necessarily in body shape, but in terms of internal structure. So for marine mammals that dive deeply, what happens there is their lungs get compressed. And as a result, this is really an adaptation to prevent getting something like the bends, because what it does is it collapses the alveoli, the little terminal air spaces where oxygen and carbon dioxide are exchanged, but also nitrogen is exchanged. By compressing them, you don't absorb nitrogen into your tissues. Okay, it's sort of kept in what we call the dead air spaces, your trachea, your bronchi. And in so doing, nitrogen is not absorbed at high pressures. And it's the nitrogen that comes out of solution when you've been breathing on scuba and come up too fast, that forms bubbles that go into the joints and blood vessels and even go into the brain. So we don't really have a shape that is in tune to that increased pressure, okay? But we do find various adaptations that animals have to deal with that pressure.
Yeah, okay. Thank you, sir.
Other questions?
Yeah.
These are all the students and the people who are left, they are all material scientists.
Okay.
So I think what you have told them is that they should look at nature, and they may see structures or mechanisms that can be copied. But now that some of them at least will start looking more.
Well, a lot of people are looking at things like shark scales,
Yeah.
how they're made, how they're organized on the body. There's a lot still with at the nano level that we're still learning about, and how that interacts with flow. So so those are also considerations. Not my area of expertise really, but I'm do more sort of micro or macro, but there are things that you can look at and the way that animals are structured to see then where you can take advantage of it, whether it's airflow or water flow. Consider there was something written not too long ago about how dandelion seeds actually get distributed in the wind, how at the level that they are in their size and such, how they worked very effectively as sort of these parachutes to disperse the seeds. And that's at a small level. And so there may be things like that. At a very small level, people have been interested in what they call owlets. These are sort of also like the humpback whale. They're little fine projections along the leading edge. We find them in owls, and what they do is that they change the aerodynamics such that they make the wings silent. And so owls, which forage at night, okay, everything's in tune, not with light, but with sound. So their prey, small mice and such, have to be, have to hear this predator coming at them. And the owl, essentially, in this sort of biological arms race, has modified its wings so it's very silent, even when it's flapping. Okay, if you've ever scared up a pigeon or a bunch of pigeons, you can hear the woo, woo, woo. You can hear the flapping of the wings. Owls don't make that sound at all. Okay, so at these fine levels, we may find that there are certain aspects. The other thing too is, from a structural standpoint, how do you actually get something to actuate? There's been a lot of work on artificial muscle, okay, a structural material. The problem being is that, yes, you can get artificial muscle, okay, but a lot of it has to be in thin layers because you need ion transfer.
Right.
And because of that, they're slow acting sometimes, or they'll only work in a particular range of temperatures. They're best in salt water because there are lots of ions to exchange, whereas not so good in fresh water. And the performance of these artificial muscles is nowhere near as good as real muscle, not as strong. You can't get the same sort of stresses developed. And you can do it with memory alloy metals, but the trouble there is you produce too much force, and it takes a lot of energy in order to get that memory alloy to actually really change its conformation. So these are things that structural engineers have to try and deal with. We're trying to emulate something closer to real muscle. And that is not just how fast it can contract or how strong it can, how fast can it relax before you can then contract it again. That becomes important. So there are a bunch of things like that. We've also looked at the surface smoothness of dolphin skin, because dolphins supposedly had ridges in their skin, and they are there, but they are very slight, and they don't really affect the drag, other than acting as a very smooth skin, almost getting close down to polished aluminum. But there has been interest in not just the scales of sharks, but the scales of fish, and how that affects the smoothness on the body, as well as the mucus content. So there's been, from a structural thing, there's been a person, Doug Fudge, who's been working on mucus of hagfishes, which when it's exuded, it comes out as sort of a little pellet, microscopic pellet. That's a coiled filament, and the filament unravels when it's exposed to water, and it sucks up the water. So you get this immense amount of slime. And I guess the Navy was looking at it as a way that if you had a bunch of this stuff, you could dump it into the water, and it could basically increase the resistance to any boat that's approaching and trying to move through it and actually stall it. So there are things like that that are being done in material science that relate to some of the things I've been talking about.
Sir, I have another confusion that what you presented in your slide, the basic aerodynamics going on in the fin. So I want to ask that what are the main causes? Like the curvy edge is the main cause, or the thickness variation? As I can see, there is a thickness variation from the edge to midway. So this thickness variation could produce the turbulence, right? What is causing the, acceleration of the flow?
What,
So,
what's causing the change in flow on our tubercles?
yes.
Okay, so, so what's happening is as the flow comes in, if it strikes the wing normally, okay, right on it, 90 degrees, okay, flow typically is going to come to a stop. Okay, we're going to have a large static pressure right there. But what's happening is because, I'll do it this way, because the flow isn't coming right on, except at the tubercle crest itself, it's coming into that trough at an angle. It gets convected down each side into the bottom of that trough. And because of that, those flows, those two flows from each side interact and form the vortices that then are paired and then convected down along our wing. And those vortices then are circulating in such a way that as we get a flow coming down in between, they're going like this, and the flow that comes in between is going in the same direction as the inside of each of those vortices. And that helps to accelerate that flow so it goes all the way to the trailing edge. If we had the flow then come off our wing at, say, a high angle attack here, where essentially we're going to get eddies and such rolling up, okay, it's going to separate. That increases the drag on the wing. That disrupts the pressure difference between the lower surface and the upper surface. And as a result, that's when we lose lift, which is something you don't like to happen, particularly if you're a passenger on an airliner.
No. Right. Well,
So,
other
sir,
questions?
What if we just make a very thinner at the edge of the flip? This,
He's saying make the flip thin.
at
May
the,
the-
at the
What will
edge,
happen then?
at the edge.
At the
Yes.
edge.
Oh, give me that again. Oh, sorry,
He's saying-
my accent's a little different.
He's saying make the edge thin. Make the flip
Yeah.
thin at the edge.
Make the edge very thin.
Yeah.
That's a possibility. We've known that tubercles work on a fairly robust cross-sectional design.
Mhm.
There has been some work on very thin, thin blade, thin wing-like structures, but not a lot. Most of the time we're using like NECA or NACA 0012s up to 0024s, nice symmetrical foil sections. But there has been some work that says that the effect applies even if it's a thin plate and you make the tubercles there.
I see. But that would create a materials problem also,
Mhm.
right? Because of that, such a structure is going to be prone to embrittlement, and fracture.
And another thing that people have been always talking about is everyone wants to go for the gold. What we've got is rigid, static, wing-like structures that are being tested, and people go, "Oh, the humpback whale flipper, it has some flexibility in it. How's the flexibility affect that?" Well, now you have to try and match the stiffness of the whale's material with the stiffness of whatever particular polymer you want to use. And then do you put in finger bones and things like that to stiffen it and provide some sort of joints? These are things that are important. So for instance, the Mantabot, okay? The Mantabot uses dragon skin. And so we have a silicon fin goes over the tensegrity structure that makes it go up and down. But when we first did it, what we noticed is for the particular mixture that they used to make the silicon fin, at the tip, we got an immense amount of flexion that you don't see in the real manta. So we've had to create a fin where there are different degrees of stiffness of the material as you go down the length or span of that fin. So that becomes an important thing in trying to emulate the motions of the manta ray.
Thank you, sir.
Okay.
All right. Well, thank you, Frank. That
Okay.
was enlightening. Thank you so much. And I will later in the day send you, I'll put it on YouTube. So
Okay.
you'll have a link also, and I'll send you a link.
Okay.
Yeah.
No problem.
Wonderful. Okay. Thank
Okay.
you.
It was a pleasure. Thank you very much.
Bye-bye.
Okay. Bye.
Okay.
Bye.
Thank you.